Hello everyone, today we do a review of power series, which we'll need for chapter 5. So this review is represented in your book in section 5.1, and I do have very nice notes, but I want to give you like voice lecture also. Okay, let me remind you. So what are power series? There are two types of power series. Power series centered at 0. So give me a second. Power series centered at 0. How are they going to look? They're going to look like a0 plus a1x, a2x squared, a3x cubed, and so on. In sigma notation, they're going to look like sigma n equals 0 to infinity, have infinitely many terms, an, a constant term, and the power of x. They're called power series because they use powers of x, right? And they just look like a very, very long polynomial. Here, an are constants. And they are going to kind of change like what the series is going to give you as an answer, right? X is going to be just a variable, a real number. X, a real number. Variable. Like a normal X in a function, right? And A is going to be like a constant, but depending on like how it looks, it's going to change what the result of the series is going to be. Now, power series centered at A. So I'm not going to copy the power series. Sorry, sometimes I touch something in the whiteboard and it makes it smaller. So power series centered at A. Well, they basically are going to look like this, except that it's not going to be just x, but it's going to be x minus a everywhere where what x. So for example, x minus a squared and so on. And in sigma notation, it's going to look like an. And instead of x, we have x minus a to the power of n goes from 0 to infinity in general. So actually power series centered at 0 are centered at a equals to 0. If you plug in a equals to 0, you are going to get power series centered at 0. We are going to mostly use power series centered at 0, but for some problems, it's necessary to shift the center of the series to a different point. So let's discuss basic ideas or like theorems about power series. First, we are going to discuss absolute convergence. So absolute convergence. Well, you know, guys, that series can converge to a number or can diverge, which means that the sum of series does not have a limit. It can go to infinity or it can go nowhere. For example, it can oscillate between -1 and 1, and this is considered also like not convergent series. So the series is convergent only if the sum of series is approaching to a certain number. Okay, so the series, I'm going to write down generally series an x minus x0 to the power of n goes from 0 to infinity, and here x0 is the center of the series, is called convergent absolutely if the series of absolute values, you take absolute value of the term of the series x minus x0 to the power of n and goes from 0 to infinity is convergent. So if you drop all the minuses from your series and it's still convergent, we are going to call it absolute convergence. Why do we call it absolute convergence? Because actually it's convergent of absolute value, right? Okay, How do we check this absolute convergence? We have a nice ratio test to check absolute convergence. So ratio test. What ratio test is doing? Well, it's going to find the limit between term n plus 1 of the series divided over term n of the series, taking absolute value because it's absolute convergence, and when n goes to infinity. For us, well, ratio test works not only for power series, actually it works for any series, but mostly people are using it for power series because power series are fitting very well into ratio test. So for us, ratio test is going to look next way. My term n plus 1 is what? A n plus 1 multiplied by x minus x0 to the power of n plus 1 divided over an x minus x0 to the power of n, absolute value, and n goes to infinity. Right, so if this limit equals to a number L, and this number L is less than 1, then the series is convergent absolutely. Now, if limit is greater than 1, then the series is divergent. And third opportunity is limit is equal to 1, then the test doesn't work. The test is inconclusive. Inconclusive does not mean that the series is divergent or convergent. It's just that it's telling the test does not fit to check this series for convergence. We need a different test, and different test usually is going to work. Okay, so 3 possibilities. Of course, we are interested in limit less than 1 when it converges absolutely. Why? Because we have a very nice theorem that if the series is convergent absolutely, it is convergent. So absolute convergence is a very strong type of convergence. If the series is convergent absolutely, it's going to be convergent by itself too. Okay, now I'm going to consider an example. Let me scroll it a little bit up and just consider an example. Maybe I choose a different color. So let's start with example 1. I'm going to consider series x minus 1 to the power of n divided over n goes from 1 to infinity. So it's a typical power series centered where? Centered at 1, right? 1 is the center of the series. We are going to see why we call 1 center of the series. And we are going to apply ratio test. I'm going to label it ratio test. That's a limit as n approaches infinity. And that's going to be what? X minus 1 to the power of n plus 1 divided over, oh, come on, not supposed to be a triangle. Divided over n plus 1. I hit something and it converts my lines into triangles and circles. Over n again, additional triangle. I don't know why it likes triangles. Okay, absolute value. Let's simplify it a little bit. Here we do have a same expression here to the power of n plus 1 and here to the power of n, which means that it's just going to be the first power, right? And I'm going to write kind of this n goes on top, and we have n over n plus 1 multiplied by x minus 1 to the first power as n goes to infinity. Well, I'm going to split my absolute value into 2 absolute values, or better, take n and n plus 1 outside of absolute value because they are positive, or you can kind of split it like this, n plus 1, and over here x minus 1 absolute value. Why? Because if absolute value of the product is equal to absolute value of the first number by absolute value of the second number, and n goes to infinity. Well, we do see that x minus 1 does not depend on n, so we can take it outside of the limit and write it down like this. So I'm taking this one outside of the limit. And under the limit, I have n over n plus 1. N goes to infinity. Well, kind of obvious that limit is equal to 1. and we have final answer x minus 1. So to make the series convergent, we will need to make this less than 1, right? To have it convergent. Well, which is going to give us inequality, right? And inequality is going to give us interval of convergence. So it's not going to be convergent for all x's, right? For example, if I take x equals 5, 5 minus 1 is equal 4, it's not less than 1. But if I take x equals 0.5, 0.5 minus 1 is minus 0.5, absolute value is 0.5 less than 1. So it's going to give us interval on x where the series is going to be convergent. I'm going to write down this interval and then kind of try to solve it, show you different ways to represent it. Well, usually when I have an equality like this, I just draw the picture, draw the number line. Sorry. No, it's not supposed to be like this. Sorry, I wanted just to erase vertical. I'm going to draw a number line, put center 1 somewhere here, right? And step 1 unit to the right and 1 unit to the left. Here we're going to have 0, here we're going to have 2, right? And I'm going to make them empty circles because actually it's supposed to be strictly less than 1. So over here, between points 0 and 2, the series is convergent absolutely. Convergent absolutely. Why? Well, because for any number from this interval, you subtract 1 and the result is going to be less than 1, like 0.5, for example, you subtract 1, it's negative 0.5, absolute value 0.5, less than 1, right? Now, for everything outside of the interval, we are going to have numbers, limit is going to be greater than 1, and it's going to be divergent. I'm going to write it down. L is greater than 1. And for endpoints, we really don't know what is going to happen because for endpoints, this one and this one, the test is going to be inconclusive because, well, consider 2 over here. You take 2 here. 2 minus 1 is 1, so it's not less than 1. It's not greater than 1. It's equal to 1, which tells that the test is inconclusive. Well, we are going to check these points, but before we do it, I want to a little bit extend this inequality and explain why I draw my picture like this. It's not very difficult to understand. I'm going to write down, you know that inequality with absolute value actually can be opened like this, minus 1, x minus 1 less than 1. If you do have inequality like this, actually it's double inequality, right? And if you add 1 on both sides, on all 3 sides, you do plus 1 here, and plus 1 here, you are going to have what? 0, x less than 2. So actually you are going to get this interval. It's just a faster way to do it. You put a center and then kind of step 1 unit to the left, 1 unit to the right. That's why we actually call it center, because that's exactly a center of the interval of convergence, right? And if you draw a circle with center in a center and going through the boundary points, you are going to see that 1 is going to be the radius of this circle, and we are going to call it the radius of convergence. But before we kind of finish discussion about the radius, let me check endpoints. Center of the series. Okay, so endpoints. Well, first endpoint is what? 0. So I'm going to just set up x equals 0 and plug it into my series directly. So how my series is going to look? Well, 0 minus 1 is minus 1. So it's minus 1 to the power of n over n. And well, n goes from 1 to infinity. And I do see that, what is this? This is alternating harmonic. Alternating harmonic. Alternating harmonic is convergent. Okay, for x equals 2, I'm going to have like 2 minus 1 is 1. So 1 to the power of n. Sorry, it doesn't look very nice. And my line doesn't look very nice. And my 1 doesn't look very nice. Let me scroll it a little bit up. So 1 to the power of n over n. This one is actually normal harmonic. And it's divergent, right? We remember that harmonic is divergent. Alternating harmonic is convergent, but just general harmonic is divergent. So if you want to know interval where the series is convergent, you're going to write on x belongs from 0 to 2. 2 is not included because the series is divergent at 2 and 0 isn't included, right? Okay, kind of simple, right? Well, again, I already talked about the radius, right? So if you draw a circle right through the center of the series, which goes through the endpoints, you are going to have a like circle with a certain radius. The radius of the circle is called the radius of convergence. Radius equals to 1. Well, radius sometimes will be equal to a number like 1, 2, or 3. Sometimes it will be equal to 0. What does it mean? That the series is convergent only at one point, at the center. Well, you know, that means that basically everything else except this one point is equal to 0. And also the radius of convergence can be equal to infinity, which means that this circle is very, very large one, and the series is convergent everywhere for all real numbers. Happens sometimes too. Okay, I'm going to write it down. I'm going to write it down. Can be 0 and or not and, I think better to say or, right? Because it cannot be 0 at the same time, or infinity 2. Okay, now we're just going to, so this is convergence, and it's important because if series is not convergent, it's not going to give us any number at the end. And well, who needs series like this? We usually are interested in series which are convergent. Now, guys, some properties of the series or how to operate with series, because we are going to deal in this chapter a lot with series and sigma notation. So I'm going to maybe choose a black color. Why not? And just describe certain stuff we can do with series. So number one, what can we do with series? Well, we can add, subtract, multiply, or divide series. And I'm going to start with addition. So imagine that you have two series of terms an and series of terms bn. It's important that the series start with same index. You can unify them into one series, an plus bn, and n goes from 0 to infinity. Well, why? Because like if you have a sum of terms here and sum of terms here, you can just combine them by 2 and add the first terms first and the second second, and so on. If you do have a minus between them, the minus is going to appear over here. So well, we can either split one series from two terms into two separate series or merge them together. Okay, let's go back. Number two, what else? What we can do as a series is to differentiate them or integrate them. I'm going to write it down, differentiate or integrate. Well, how do we differentiate series? I'm going to show you the derivative. So, well, I'm going to consider very kind of general. Series was centered at 0. It's not going to change anything if you center it at any other point. So we differentiate it, and we just take a derivative of every term. So you just bring the derivative inside, like an x to the power of n, differentiate inside. Again, you can do this with convergent series only. And just a is a constant, x to the power of n is a power function. We differentiated it by the standard rule, right? N x to the power of n minus 1. And now, guys, if I start my n with 0, what is going to happen to the term 0, by the way? How this series looks? looks like a0 plus a1x plus so on, right? If I differentiate the constant, I'm going to get 0. So actually my 0 term is going to disappear. So my new series is going to start with 1. If I keep 0 term, I'm going to get some kind of nonsense because you know the derivative of constant is equal to 0, not equal to 1 over x. If you put over here 0, it's going to give you x to the negative 1 power. Multiplied by 0, but still a little bit tricky, right? Okay, good. So differentiation is described. Now integral. How do we integrate series? Well, again, let's consider a series under the integral sign, an x to the power of n from 0 to infinity. So what we can do, guys, we can bring the sign of integral if the series is convergent inside of the series and just integrate it as a normal power function. So an is a constant, right? And x to the power of n is going to increase the power, and you divide by n plus 1, and you have a series starting with n equals 0 to infinity. And basically that's it. Just don't forget that whenever you integrate anything, you are going to add a constant here. And another important thing here that because when n equals 0, you're going to have 1 here and 1 here. So it's going to look like your series starts with 1, 2. You don't need to shift the index, but sometimes you are going to see that people are going to shift the index. They are going to write down instead of n plus 1 n and start it with 1. But if you just write down first few terms, you are going to see that the series are identical. Okay, so I'm writing down what I did. Okay, now what else can we do with series? Well, important thing, if the sum of series an xn and from 0 to infinity equals to 0 for all x where it's convergent, then a0 equals a1 equals a2 and so on. So all a's must be equal to 0. So if some sum of series equals to 0, it's not going for any different x. For x equals, for example, 1, 2, 3, 4. Of course, x must sit in the interval of convergence. Then there are no option for this series to be equal to 0. Otherwise, some coefficient be equal to 0. We are going to use this property a lot. Well, again, if any coefficient is not equal to 0, it's going to give non-zero term, which is going to participate in making this non-zero. Let's move to number 4. We're going to talk a little bit about Taylor series. If you have a differentiable function, if f of x is well, supposed to be infinitely time differentiable function, but we can kind of say n time differentiable function. Differentiable. For this series, we will need it to have like infinity time differentiable function. And f of x can be represented as Taylor series, which is going to look like this. F and derivative at point x0, x minus x0 to the power of n, and divided over n factorial. And this is kind of the formula which is going to represent any infinitely many times differentiable function. Of course, to make sure that the series exists, we'll need to have the first derivative, the second derivative, and all other derivatives exist. Okay. Well, what is Taylor series? It's expansion of x function over the vectors. If you still remember a little bit of linear algebra, Taylor series can be considered as an expansion of f of x over the vectors. Let's consider vector set 1, x minus x0, x minus x0 square. If you still remember linear algebra, you probably remember that you had sets like this. So it's kind of you find the coordinates of this vector in this vector space. And this is going to be like a coefficient. So I'm going to write down with and the derivative at x 0 over n factorial coordinates or coefficients. Okay. Next thing we want to learn is like when function f of x is analytic. Sorry, a little bit wrong. Well, again, function f of x is analytic at x equals x0 if it has a Taylor series extension. Why don't I write an extension over here? For example, e to the power of x, you still remember how Taylor series is looking, right? Sigma x to the power of n over n factorial, n goes from 0 to infinity, which is 1 plus x squared over 2 factorial plus x cubed over 3. Okay, I don't need a triangle here. Again, no triangle. 3 factorial and so on. So that if you can represent the function as Taylor series, it's analytical. Next one is how to shift the index of summation. Number 5, shift of the index. I think I'm missing something here. Is this index of summation? How to shift the index of summation? Well, imagine that you have a series a n x to the power of n centered at 0, which starts at 5, goes from 5 to infinity. How do we move it to like series which starts at 0? Well, we're going to introduce a new index, m equals n minus 5, from which n will be equal m plus 5, right? And we are going to convert all my n's to my m's. So let me start. A, instead of n here, I'm going to write down m plus 5, x, m plus 5. Now, my n here starts with 5, right? When n equals 5 here, it's 5 minus 5, m starts with 0. And m starts with 0 and goes to infinity. So that's how we change index of summation. Let me give you an example. N x n minus 1, and from 1 to infinity, I'm going to shift my index of summation and set m equals n minus 1. So n equals m plus 1, right? And I'm going to write down everything in terms of m now. So instead of n, I'm going to write down m plus 1 here. Instead of n minus 1, I know that it's m, right? And when n equals 1, my m is going to be equal to 0. M equals to 0, 0 to infinity. So I shifted my index of summation. After you shift index of summation, you can return back to your original summation index. You don't need to actually have a different index. So you can right after that, you can go back to n and you can write down n plus 1 x to the power of n and from 0 to infinity. It's just like a index of summation, which is kind of default one. So you can label it n or m, or whatever you like. Okay, now what else we need to know about the series? Let me shift it up. Yeah, it's kind of long lecture because it's not only like we are reviewing properties of series, but also we are reviewing properties of sigma notation. How to multiply series by x to the power of r. By x to the power of r. This is not n, that's r. For example, x cubed multiplied by x to the power of n goes from 0 to infinity. Well, you just bring x cubed inside and you have x cubed by x to the power of n goes from 0. And then just because they're same base, you just can write down x n plus 3 n from 0 to infinity. Okay. Now, kind of a little bit more complicated thing. Manipulation with coefficients to solve series equations. It's going to take a while. Number 7. Sorry. To solve series equations. Well, for example, guys, you have the equation in series, how it's going to look. Typical one. N, A, N, x to the power of n minus 1, n starts with 1 to infinity, minus series A, N, x to the power of n goes from 0 to infinity, and equals to 0. How do we know it's an equation? Well, it's just like equals to 0, right? Whenever you have equal sign, it's an equation, right? What are we searching in this equation? We are not solving this equation for x. X is just variable. We are solving this equation for an. Solving for an, not for x. Not for x. Okay, so actually this equation is supposed to be true to every x where the series are convergent. So we're not solving it for x's, we are solving it for n. What we are going to do, guys, I want to shift the index because I cannot add these two series together because they start with different numbers. The first one starts with 1 and the second one starts with 0. I'll need to kind of maybe shift both to 0. So I'm going to deal with this one. Let me change the color and maybe make it thicker. So I'm going to consider this one and shift the index for this one. So what I'm going to do, guys, I'm going to consider m equals n minus 1 and kind of shift the index for this series. So how it's going to look? Well, n equals m plus 1, right? So I'm going to write down m plus 1 here, a m plus 1 here, and x to the power of m, right? And when n equals 1, m is going to be equal to 0. So I shifted the index. Now, because I want to deal with same index name n, I'm going to go back to n. So I'm going to write down n equals 0 to infinity. Again, index is just kind of, dummy variable, let's say. Sorry, instead of. So after you shift the index, you can return back to your original number. Now, my series number 1 starts with n equals 0. My series number 2 starts with n equals 0. So what I can do with them, I can unify them under one sigma sign. So I'm going to write down n plus 1. Oh, come on, I don't need a circle. N plus 1, a n plus 1 x to the power of n, my first series, minus a n x to the power of n, my second series, and n goes from 0 to infinity. It's supposed to be equal to 0. So again, what I did over here, I just renamed my m as m, right? Now, what I'm going to do, guys, I'm going to take xn, which repeats here and here outside of parentheses, and kind of have a coefficient. Coefficient is n plus 1 by n, an plus 1 minus an. The coefficient is xn, starts with 0 to infinity. I'm going to recall one of the properties we had, right? Property number 3. In property number 3, they were telling that if series is equal to 0 for all x, then the coefficients must be equal to 0, which is going to give me equation on coefficients. So I'm just going to write down the equation. It's n plus 1, an plus 1 equals an, oh, not equal, minus an, sorry, equals 0. So that's my kind of equation, which I'm going to solve for n plus 1. So n plus 1 equals an over n plus 1. This equation is called recurrence formula. Well, if you do know like previous coefficient, you are going to do know next one by just plugging into the formula. Well, we actually don't know what is the first coefficient 0. We're going to assume that it's kind of some unknown constant. So I'm going to start calculating. So what is going to be a1? A1 is a0 divided over 1, right? 0, 0, a0 divided over 1. A2 is a1 divided over 2, right? Because if I plug in 1 here, 1 here, 1 here, it's 2. Or if I plug in a1 over here back, I'm going to get a0 over 1, 2. A3 is a2 over 3, which is a0 over 1 over 2 over 3, right? And I'm going to write it down like a0 over 3 factorial. Sometimes it's going to be like easy to see, sometimes not. But I can get all the coefficients and basically I solved my equation. So solution of this equation is going to be a certain series with coefficients, which are going to be like a0, a0 over 2 factorial, a0 over 3 factorial. I'm going to write down the answer, okay? So the series is going to be a0 over n factorial and x to the power of n goes from 0 to infinity. So I solved actually this series equation and found the coefficients. A0 is unknown constant. Maybe there are going to be some other condition which define them. Right. Now, guys, a few words about useful series. Okay. Number 8, useful series. The series which you probably want to remember, e to the power of x, sigma notation, x to the power of n over n factorial, n from 0 to infinity, or 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Okay, cosine of x is going to be -1 to the power of n, x to the power of 2n over 2n factorial. Again, n starts with 0, goes to infinity, and if you kind of write it down like that, without sigma notation, it's 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial, and so on, alternating series with even powers. Too many, actually. Sine of x, a very similar series, a very similar -1 to the power of n, but here x to the power of n plus 1 over 2n plus 1 factorial, n from 0 to infinity, and equals x minus x cubed over 3 factorial, again the unnecessary triangle, 3 factorial plus x to the power of 5 over 5 factorial. Okay. And minus so on. So alternating series with odd powers, right? Just one more series. This is G series, geometric series. 1 over 1 minus x, which is 1 plus x squared plus x cubed. You see all coefficients are equal to 1, and sigma notation is very simple, x to the power of n goes from 0 to infinity. Okay. Now, guys, we already kind of know everything about series. The question is, why do we need series, and why are we kind of reviewing them in this chapter 5? We are going to use power series to find solutions of differential equations where no other methods are working. Change the color, maybe should use blue again. So what does it mean? I'm going to show you one example of solving differential equation with use of power series. Use of power series to solve differential equation. Well, guys, I'm not going to solve super complicated differential equation because I want to solve something what is familiar to you, for which you actually do know a solution. But normally series are not used for these cases. Series are used for the cases where no other solution exists. Okay, so we're going to start with example y prime minus y equals to 0 and y of 0 equals to an initial value problem. What is the solution of this initial value problem? We do know that solution is y equals e to the power of x. Well, just plug it in over here. Simplest equation, right? You do separation of variables, characteristic equation, like lots of methods are going to give you the same answer. E to the power of x, derivative minus e to the power of x equals to 0, and e to the power of 0 is equal to 1. So that's a solution. I'm going to write down solution. Now, let's see how the series is going to work with this. Okay? How power series. Okay, I'm going to start searching solution of my equation as a power series an x to the power of n. Oh, sorry, I'm going to consider cn actually instead of an. Cn n to the power of n, x to the power of n from 0 to infinity. So my goal is to determine the coefficient cn. What I'm going to do, guys, I'm going to differentiate my power series. Sorry, link it up. So y prime. Well, I'm using standard differentiation rules. So it's Cn derivative of x to the power of n. It's n x minus n minus 1. Starts with 1 to infinity. And kind of put it into differential equation. So the first series is going to be sigma Cn n x n minus 1. N goes from 1 to infinity. Sorry, n minus 1 doesn't look very nice. N minus 1 minus Cn x to the power of n, and from 0 to infinity equals to 0. Well, what I'll need to do, I'll need to shift the index to add them together into one sigma notation. So I'm going to do the shift of the index. So I'm going to call m equals n minus 1. So that's cm plus 1, right? If m is n minus 1, then n is m plus 1. M plus 1 x to the power of m, and if n is equal to 1, m will be equal to 0. So I shifted it. Now I'm renaming index to go back to n. So cn plus 1. By the way, guys, if you do see how to do this without kind of introducing a intermediate index, you are welcome to do it. It's not very difficult. You just kind of look at it and shift everything one unit. Okay, now I'm going to plug this series back into here and sum it up with this one, So what I'm going to have, I'm going to have 1 sigma, and here Cn plus 1 from the first series, n plus 1 x to the power of n, and from the second series minus Cn x to the power of n. N supposed to be equal to 0, and n goes from 0 to infinity. Well, again, I'm taking x outside of parentheses and have a coefficient Cn plus 1, n plus 1 minus Cn x to the power of n equals 0 to infinity. And now the coefficient must be equal to 0 to turn this into a true statement for all x's, right? Well, I'm going to just kind of set Cn plus 1 by n plus 1 equals Cn, right? I move this to the right side, and Cn plus 1 from where equals Cn over n plus 1. We basically already seen this series, right? We already know how to calculate everything. So I'm going to start with calculating coefficients. So C1 equals C0 over 1, C2 equals C1 over 2 or C0 over 1, 2 or C0 over 2 factorial. And C3 is going to be, you can guess, C0 over 3 factorial, and so on. Well, you just kind of repeat the steps and extract all the C's starting with C0. Now, we're going to go back to the series. Back to the series. The series was looking like this. Y equals Cn x to the power of n from 0 to infinity, right? Now I'm just going to plug in my Cn's, right? So they are going to be C0 over n factorial x to the power of n from 0 to infinity. C0 is same for all of them. You can take it outside of the sigma notation. C0 sigma x to the power of n over n factorial. Well, a triangle again. Come on, stop drawing me triangles where I don't need them. N from 0 to infinity. And we do remember from my table of the functions that this is e to the power of x. So we do have C0 e to the power of x. Now we just need to find C0, right? We are going to use initial values. Y of 0 equals 1, which means that 1 is equal to C0 e to the power of 0, which means that C0 equals to 1. And my solution is the same familiar solution, y equals to e to the power of x. So the series is producing same solution. I'm trying to say here that series is a reliable method to use for solving differential equations, not very difficult to write. You don't need to invent anything. You basically just kind of get relation for the coefficients. Of course, no one is using series to solve simple equations like this. Usually, guys, people are using series to solve more complicated equations. Some differential equations don't have any other solution besides a series solution. Here we got the series solution, but we know that this series is actually e to the power of x, right? But some equations, like Bessel equation, is going to have a solution, series solution, which cannot be converted to any function because that series is a function actually, and we don't have any other description for this function. So we call Bessel functions, but actually they are Bessel series, okay? So that was a little introduction. And my suggestion to do the homework, practice a little bit with sigma notation because we are going to have it a lot, like in next 2 days. Okay. And that's it. Thank you for your attention.